You can go ahead and get started here. Okay, thank you all for coming. I am very excited to introduce Dr. Lachlan Lancaster, who is visiting us here from Princeton University, from Columbia, excuse me. Lachlan did his master's degree at the University of Cambridge, and then his PhD at Princeton University, and he's now a junior Simons Fellow at Columbia University. And he's an expert in a lot of aspects of star formation. I'm very excited to hear what you have to tell us today. So please take it away.
Thank you, Anuj. Yeah, so I said this morning that the Astro Coffee that I put everything into this talk, so I may not have time for all of it, and I apologize for what may be a whirlwind, but please stick with me. Yes, a wind, definitely. To give you guys, I'm going to talk about or get to this and start off with a nice little schematic that will hopefully entice you to keep paying attention until I get to this crazy point. This is what I'm showing you in the background is the H-alpha surface brightness from one of my simulations of just a photoionized gas cloud in a photoionized bubble expanding into a messy, turbulent gas cloud. And here's what that same bubble looks like when you include a stellar wind bubble blowing into that, as well as the photoionized gas. If you don't understand everything that I'm talking about, I'll explain. But you see that large change in the surface brightness and the structure of the H-alpha emission because of the presence of this hot X-ray emitting gas that's in the center of this. So we'll hopefully get to all of that. Give you a quick outline. I'm going to review a lot of my work on wind-blown bubbles in star-forming regions, then talk about this coevolution that I promised, how to think about the coevolution of wind-blown bubbles from massive O stars and the photoionized gas that's created by their hard ionizing radiation, then the regimes and evolution of the model, comparison to simulations, and then the consequences for the observations. To start from very, very broad up top, we have star formation in galaxies. We know that it occurs within molecular gas. It is, on a galactic scale, just extremely well correlated, the star formation surface brightness with the molecular gas surface brightness. The sort of relationship between this gives you an idea of the time scale at which star formation proceeds within galaxies. That's sort of on the large scale. When you look on the very small scale, you almost always see newborn stars, young stellar objects in the centers of lots of dense molecular gas. And one of the ways that, as a theorist, we like to think about or sort of segment these scales between sort of the large scale galaxy and the small scale individual forming clump of young stellar objects is the so-called clouds of molecular gas, which you can kind of think of as following some sort of mass function with some power law. Because of the slope of the power law, most stars are formed in quite massive clouds of maybe 100,000 solar masses or above. And I say that because I think a lot of the times people talk about most clouds being much less massive, maybe 10 to the 3 to 10 to the 4 solar masses. That is most clouds because they're up here, but most stars form over here. So I'm most concerned with the most massive clouds that form most of the stars. They're the most important for star formation. But the idea of a cloud is fake, right? Density in the ISM has a multi-scale sort of fractal nature. Cloud sizes in observations are often very well correlated with the observational resolution of the study that you're kind of looking at these things are, but it's still an important theoretical sort of mindset in which to consider star formation. So that's just my honest telling of the perspective from which I'm coming at here. So that the basic question we have is, if we start off with a cloud, this is the very theoretical picture. We start off with a cloud of gas with some constant surface density. We put in some turbulence and gravity, and we allow that cloud to collapse under gravity, form stars, and be disrupted by feedback from those massive stars. How does that process proceed? What are the most important aspects? That's sort of the fundamental question of lots of my research. So as you might expect from what I said, the basic picture is you have the cloud, it's collapsing under its own self-gravity. You have various forces that are acting to prevent that collapse, but they don't really just prevent that collapse so much as lead into one another. And in particular, sort of at the heart of that is feedback from the actual formation of the stars. You form, particularly in these most massive clouds, you form a few very massive stars. And it's really because they're massive enough, they have very high energy radiation fields in their atmospheres that are powerful enough to disrupt the cloud in many different ways, either through driving through gas pressure, turbulence, magnetism, sort of feeding into each of those things. So when I'm talking about feedback from these individual massive stars, all of this comes at its root from the strong radiation fields in their atmospheres, but that can affect the surroundings in multiple different ways. We have stellar winds, which I'm going to talk a lot about. That's basically you have a strong enough radiation field that you are shedding your own atmosphere. You're line driving winds. And because the escape velocities of these stars are maybe 1,000 kilometers per second, the winds end up being 1,000 kilometers per second. They run into the surrounding gas and shock heat to 10 to the 7, 10 to the 8 Kelvin. So super, super hot bubbles. Photo-ionization heating, you have these hard ionizing radiation fields from these stars. The photo-ionizing radiation ionizes the surrounding molecular or atomic hydrogen gas. That heats everything up to maybe 10 to the 4 Kelvin, which is much, much hotter than the surroundings, therefore much, much overpressurized, and that pushes everything apart as well. I won't talk about these. This is radiation pressure mostly on dust grains, a little bit on individual atoms as well. This is infrared radiation pressure bumping around and pushing things out as well. And this is Lyman alpha scattering, which is very uncertain, but may seem to be, I won't talk about that at all, but you can ask me about it. So first of all, let's talk about stellar winds. Yeah.
So in the galactic context, we start off with the elements of what becomes a molecular cloud, unbound with respect. So there's a process by which this stuff becomes bound. In some sense, it has to lose energy in some frame in order for that to happen. And so can that process really be, just a very general question, separated from the process of feedback? In the sense, that you're assuming that one stage has happened, then you have the energy release.
Can it be totally separated? No. No, the universe is messy. But what I was trying to, with the sort of the first part, I'm trying to at least say, I'm sort of ignoring those complications and putting myself in this nice theoretical picture that I can hopefully explain. But you're right. I mean, the way that you lose energy and become bound is mostly through cooling. This gas is quite efficient at cooling. I mean, how you get stuff close enough that it becomes bound is maybe through turbulence driving on large scale. There's lots of debate about how that.
Well, I guess what I'm just wondering about is you have some energy loss that let the gas become bound. But are your calculations including energy loss?
Yes. So the simulation that I just showed you starts out as a marginally bound cloud that has a full suite of heating and cooling processes included that allow for the energy loss and collapse. Yeah. How that perfect cloud got there in the first place, I'm ignoring. But all of the subsequent evolution, it's marginally representative of real clouds that you would see. There's some debate there, obviously, but I can't. In this setup, I can't perfectly recreate it.
I'll ask you after.
Yeah, sorry. So stellar winds. Why do I want to care about stellar wind blowing bubbles? Well, and I say I've put all of this in the context of massive star winds in star forming regions, but a lot of the stuff that I'm going to say about this is also applicable to AGN-driven winds or super bubbles driven by lots and lots of supernova within galactic disks. The thing the reason why we care about this for star-forming clouds is that if you take a classical model for how these wind bubbles should affect their surroundings, the wind should be super dominant at disrupting these clouds. Way more dominant than photo-ionization feedback or any of the other things that I listed. But when you go and observe wind-blown bubbles in massive star-forming regions, the X-ray emission is how you see this 10 to the 7 to 10 to the 8 Kelvin gas. The pressure you infer in that X-ray emitting gas is much lower than you would expect for this classical solution, which tells you that there has to be a lot of energy being lost. So the classical picture, as I was laying out, is sort of you have winds being blown from your perfect point source of a massive star. It free streams of this free stellar wind. It's thousands of kilometers per second. Shock heats against the surroundings. You get this really, really hot shock stellar wind. The ratio here isn't exactly to scale, but you get this really hot gas that's much, much overpressurized with respect to the surroundings, and it pushes on the surrounding ISM, sweeping up this shocked shell of ISM. And in particular, in this sort of idealized approach, you have this perfect contact discontinuity. There's nothing that moves between no heat or energy transfer across the surface. And so you keep all of the energy inside this bubble very efficiently, and it blows into its surroundings. It disrupts it very quickly. If you allow for some heat transport across this, you can conductively evaporate mass into the interior. So you're basically heating this cold gas enough that it heats up to the temperatures that are similar to the interior temperatures here. Once you get that density high enough, it can cool. And so that gas itself cools quickly, and you no longer have sort of this hot shocked gas, but this hot shocked stuff kind of disappears and it becomes more of this momentum driven solution. But for typical star forming regions, that takes too long for normal processes. And the problem is, like I said, we see that the energy in these wind-blown bubbles is much lower than you would expect from the sort of classical energy-driven solution. What's more is that if you had an energy-driven solution, so here I'm showing the star formation efficiency that you would need to disperse a cloud for a 100,000 solar mass cloud, so the same sort of clouds I was talking about, as a function of the radius of the cloud. So this is basically just varying the surface density of the cloud. In an energy-driven solution, you don't need very much star formation efficiency at all in order to disperse the cloud. So if I'm talking about a 100,000 solar mass cloud, typical Milky Way GMC, maybe 10 to 20 parsecs in radius. The star formation efficiency you'd expect like fractions of a percent, right? But we see 1%-ish star formation efficiency in these clouds. That's much more consistent with this momentum-driven solution. And same thing for the momentum that's put into the surrounding gas in this energy-driven solution, which are these dashed lines. This is basically showing 3 different star formation efficiencies, 3 different powers of the stellar source that's driving this bubble. Energy-driven solution, you get lots more momentum than if you have this momentum-driven solution. So we want a way kind of recreating this momentum-driven solution without just appealing to this sort of classical conduction evaporation front. And so the basic picture is, and this was the work of my thesis for the most part, is that turbulent mixing at the interface between, so if you take away the fact that this is a perfect contact discontinuity, nothing can move across it, and you replace that with a turbulent radiative mixing layer, where you mix this 10 to the 7 Kelvin gas with 10 to the 4, in these original simulations, and more like 10 to the 2 Kelvin gas, you get gas that can cool very, very efficiently. And the basic question is, can that be efficient enough to make these wind bubbles momentum-driven rather than energy-driven? So this is a 2D slice through a 3D simulation showing the gas density, gas pressure, the cooling rate density, and this will be showing the wind mass fraction. So we can see, oh, good, that's good. We have this extremely, so I put it into this turbulent, messy background. So you see this very, very messy, multi-scale interface between the hot, overpressurized gas and the surrounding low-pressure cold gas. You see all of this, lots and lots of cooling happening at this mixing interface, and sort of the mixing process being captured by this passive scalar, which is the wind material.
Can you tell us what's in the physics of this simulation?
Yes, these simulations are pretty old. So this is a CIE cooling curve, pure hydro with a wind source storm. Yeah. So
No conduction.
sorry, no conduction. Yeah. I will get. You could put in conduction. It would be. I hope I will convince you that it would be folly to do so. Okay, and I'll explain why. So what you see in these simulations, again, these colors are representing sort of the power of that source at the center of the simulation, low wind energy up to very, very high wind energy. If you compare that to, this is the total radial momentum carried by those bubbles as a function of time, compared to what you would get if you had a purely momentum-driven solution. Purely momentum-driven, I mean that the total radial momentum carried by the cloud is, imagine this is 1, the momentum input rate of the wind, which is the mass loss rate of the wind times the velocity of the wind. It's literally just the wind running into the surrounding gas times time. They're very close to that momentum-driven solution, but you see that there's this, I'm allowing for some momentum enhancement factor, alpha p, which I'll write here, which is sort of this difference between the purely momentum-driven solution and the actual simulations. I'll also say the different line styles here are 3 different resolutions, 128 cubed up to 512 cubed, and here everything looks very nice, very well converged, which is great to see. We wanted to get an idea of if that makes sense, that these things really are in this efficiently cooled regime. So you can measure, we'll get to sort of the better version of this, but you can measure sort of the effective rate at which you can mix gas into this surface and compare it to the rate at which hot gas is being provided to the surface by the shocked wind. And in each of these simulations, these things are basically equal to one another. And what that's telling you is that the properties of this mixing layer are basically acting as a new boundary condition on the flow, the structure of the flow in the interior of the bubble. The structure of the shocked gas, how the velocity evolves with radius, where the shock exists, is based on the properties of this mixing interface. Okay. I'll quickly run through why. Well, so this is just a very basic picture as to why that would be. You guys might remember a classic calculus problem where you have a big tank full of water, you have some faucet filling it up, and if you have nothing else, it just fills up, right? But if you put a hole in it, it initially drains faster than it fills, but the rate at which it's draining is dependent on the weight of the water. Right? So if it's draining faster than it fills, it goes down until it reaches a steady state where the rate at which it's draining is balanced by the rate at which it's coming in. Why am I talking about this? Well, you can think of the tank as a wind bubble, the faucet as the wind source, and the water is sort of the energy that's being contained within it. So the whole is this cooling mixing layer that's kind of determining the boundary condition. Energy goes up in the bubble, then the pressure increases. If the pressure increases, the cooling rate in this mixing layer increases, and you have to balance these effects against one another in order to have determine the amount of energy. So that's sort of a way of walking you through this complicated, somewhat complicated equation, which is that you can basically use the properties of the mixing interface to determine what this momentum enhancement factor should be. In particular, it depends on this average velocity at which you can move hot gas across this interface, which is basically a diffusive velocity, and the area of the bubble compared to what its area would be if it were a sphere. So this is basically telling you how fast are you moving hot gas into this mixing layer, and how much of the mixing layer do you have to move hot gas through. But putting these things together determines this momentum enhancement factor. And what I want to emphasize is that it is not necessarily momentum driven, right? If I were to say that things act like they're momentum driven, that means that I want this thing to be basically constant, right? But these things don't have to be constant. They can evolve in time. And the fact that they look like they're constant in the simulations that I've shown you is a coincidence, kind of. Not really a coincidence, but kind of a coincidence. If I take two simulations with different momentum input rates, so the p dots that I put in from the wind source, but they have the same mechanical luminosity. So I'm basically just changing the mass loss rate of the wind. Basically, they have the same, this is the output momentum, the actual momentum carried by the bubble in the simulations, and these are what the momentum evolutions would look like if they had momentum-driven solutions with alpha p of 1. So they don't follow this. They have nearly the same, nearly momentum-driven solution, but they have different momentum enhancement factors because that momentum enhancement factor is being determined by the properties of mixing at this interface, which are basically the same between these two simulations. Cool. So you can then ask yourself, coming back to sort of my interpretation of what Chris was asking rather than what you were asking, what would it take to resolve the properties of this mixing layer correctly? So if you want to resolve this boundary layer, which is, as I've explained to you, determining all the physics of this bubble, you need to resolve the dissipation properties at this interface. If you include conduction, and you want to appeal to real thermal dissipation, this is just hot stuff hitting cold stuff and heating it up, in particular electrons, hot ionized electrons, then the scale that you need to resolve is the field length. This is the scale on which heat transport by thermal conduction is balanced by radiative cooling. That's this represented by this burgundy line. I'm sorry, I have a penchant for putting together complicated plots that put together too many things. What I'm showing you here is as a function of the pressure of the bubble. So up here is really high pressure, really small bubble. Over here, low pressure, really big bubble. So the bubble would move evolving this way. This is a bunch of different scales as a fraction of the bubble radius, okay? The black line is showing you my highest resolution, delta x, my highest resolution element in all of my simulations. These are different dissipative scales, okay? So this is the field length, as I was just explaining, and this is the cooling length, which I won't have time to explain in depth, but it's basically the length scale you would want to resolve if you wanted to believe that turbulent dissipation was well resolved within your simulations. And as you can see, unfortunately, this is sort of the range of pressures I'd like to resolve in my simulations. Throughout this regime, you're orders of magnitude off resolving any of these scales. So if you could include conduction, but it wouldn't change anything in these simulations because you're not resolving the scales you need to be resolving. It would slightly change the nature, some numerical things, but it wouldn't really change the impact. And what this leads to is that when you run, if you put magnetic fields into this problem, you observe that when you go from low resolution to, if you just ran two low resolution simulations, so I'm showing hydro in blue, MHD in green. The low resolutions are sort of in the middle, the lighter colors, the darker colors are the higher resolution. In hydro, you go to higher resolution, you get less momentum out. In MHD, you go to higher resolution, you get more momentum out. And the reason for that is because of these competing factors. You have dissipation, which is changing as a function of resolution because it's numerical, because you can't resolve real dissipation. And you have the surface area of the bubble, which has a fractal multi-scale geometry, which is also changing as a function of resolution. But when you include MHD, the power of the magnetic field, the strength that you get in the wind bubbles will shut off small scale instabilities and make your bubble a lot less fractal. So here's the 3D rendering of the hydro bubble, extremely multi-scale fractal. The MHD bubble, much, much smoother. And because, this is sort of explaining the fractal geometry, because the dissipation basically acts the same, you can put all of this together based on measured quantities from the simulations in order to explain the difference in the scaling behavior that you see here. So that's all very sad, but you can also predict how this bubble would act if you actually did resolve all of these things, at least in a hydrodynamical context. If you believe that turbulent dissipation drove all of the mixing at this interface, and you accepted some fractal geometry for the bubble, it turns out if you use the numbers that you think should work for this, then you still get a momentum-driven solution. So that's very nice to not, my previous work still makes sense in the context of the sort of resolved theory, at least. But this is only really justified without magnetic fields, because the magnetic fields both change the fractal nature of this interface, and they also change the nature of turbulent dissipation across the interface. Not only do they change the nature of turbulent dissipation, they also change the nature of conductive heat transport. So MHD makes this whole problem much, much, much harder, as always, but unfortunately, we can't avoid magnetic fields. I'm going to now get into the evolution of stellar wind bubbles and photo-ionized gas. Leave the takeaways from this first part up if anybody has any quick questions. Okay. Yes.
Just trying in those MHD simulations, what kind of, do you start from any particular initial conditions? Is there sensitivity to that?
Yeah. We used I think just critical mass to flux ratio to motivate a mean uniform magnetic field that's then stirred up by the background turbulence to be pretty messy. I played around with that a little bit, but it does change sort of where you shut off the fractal scale as a function of time, but it doesn't change the overall result.
Quickly ask about what's happening to the energy. So the energy is being lost by cooling, which happens fast enough because of the turbulent mixing at the interface. And the magnetic fields are inhibiting that mixing. So does that mean that the amount of cooling is significantly diminished by including the magnetic fields?
Yes, but both of the amount by which it is reduced is a resolution-dependent statement. Yeah. In both cases, we want turbulence to be driving the dissipation, but in these simulations, you are not resolving the scales at which you would expect that to be actually resolved. So what's actually driving this is numerical dissipation. And when you basically make that surface, which was more turbulent and more believable as a turbulent mixing layer in hydro, much more laminar, you see that it's just turbulent. You're taking hot gas right next to cold gas, and it's just the Riemann problem with that interface that's artificially mixing things. And the nature of the dissipation in that problem determines all. Cool. A little sad, but hopefully a word of wisdom to all.
Is there any feedback process you can identify in the sense that you push the interface faster, perhaps effective gravity and the acceleration of the interface would be higher, and therefore, say, Rayleigh-Taylor would be stronger, and you get more mixing and more limitation of the acceleration. Is there some, because otherwise, it sounds hard to get a converged description.
I can't think of anything that would do that. Winds are pretty, on the scales at which winds are important, they're kind of the dominant thing. There's nothing that really pushes faster. I'll get to my solution to this, which will, sorry, yeah, okay. Hopefully. So I guess I have that at the end here. Oh, no, I don't. I think that the answer to this is to run extremely high resolution zoom-in simulations of mixing layers, and from that to develop a subgrid model for how turbulent dissipation should work at these places. So that's my plan. I'm not sure I'm going to have time to get to that yet. Okay, so now I've explained in depth stellar winds and all of the hard problems with it. I should mention, really actually emphasize that, because that is the way forward on actually resolving that problem, is understanding this turbulent dissipation, because you're never going to resolve it in a global simulation. You have to have some sort of subgrid model for it. But now let's get to what happens when you put these the stellar winds together with photo-ionizing gas. So imagine that I have some background mean density. Now I'm in even more idealized land than the messy pictures I was showing before. You have some massive stars that are born instantaneously for my purposes, and you very quickly ionize the surrounding Stromgren sphere of gas, which is determined by the rate at which you're emitting ionizing photons, the recombination rate, K-speed recombination rate, and the mean density of the background gas. That happens on roughly the recombination timescale of the surrounding gas, which for sort of typical Milky Way conditions is something like 1,000 years. So relatively very short timescales. Considering the wind bubble acting at the same time, it expands. It doesn't have any of this complicated cooling stuff happening until the gas that it's interfacing with is cold. And the gas that it's interfacing with is only cold once it can cool, because when the wind bubble is initially expanding, it shock heats all the gas that it's interacting with up to very high temperatures. But eventually, actually after a very short period of time, that shell of gas surrounding the wind bubble will cool, and that happens in roughly 500 years. So again, extremely short periods. Both of these things have about the same density dependence and about the same time scale, where you can basically picture these things as happening at about the same time. Yes, again, we'll come back to the momentum enhancement factor. So you can sort of picture your starting point as this, some photo-ionized gas with some embedded windblown bubble, and then you want to ask, is the presence of each other at this point sort of affecting one another significantly? Well, the dynamical expansion time of the photo-ionized gas is basically this. That's quite long compared to both of the timescales that we were talking about. So the photo-ionized gas hasn't had time to expand yet by this point, which means that it's kind of, this hasn't evolved very much. Has the wind bubble then had a chance to affect the photo-ionized gas? As it sweeps up and it forms the shell is quite dense. It can recombine much more quickly than the surrounding gas, which means that it can trap ionizing radiation and potentially draw in this ionization front very quickly. But it turns out that that only happens at extremely high densities. So that is not quite as important. So basically what you start off with is this overpressurized wind bubble. This is the pressure of the wind bubble at the time of shell formation. It's much, much overpressurized with respect to the photo-ionized gas, and the photo-ionized gas is much, much overpressurized with respect to the surroundings. So for a while, they kind of evolve almost as if they didn't know about one another, until you reach a point where the wind bubble has expanded to a point where it's basically at the same pressure as the surrounding photo-ionized gas, and now the presence of the photo-ionized gas matters to the evolution of the wind bubble. It's feeling the surrounding pressure of the photo-ionized gas. So I now want to talk about, sort of, now that I've explained this, that equilibrium radius, the time at which they're sort of in pressure equilibrium with one another. I'm going to use that as sort of a way to lay out the space of this coevolution, how wind bubbles and photo-ionized gas affect one another. So on the y-axis here, I'm showing you that equilibrium radius as a fraction of the Stromgren radius. So this should be up here. Winds are very, very important. Way down here, photo-ionized gas is dominant, and winds are not affecting it very much. On the x-axis, I'm showing the Stromgren radius as a function of the cloud radius. So over here, you should never really see anything because you just immediately ionize a cloud as soon as you form stars. You shouldn't really get to that point. And this is kind of just an unrealistic part of parameter space. But what I can do is take a bunch of different cloud masses. So here's 10 to the 4, 10 to the 5, 10 to the 6, and vary their volume density. So this is very low densities here up to very high densities here. I can use there are a bunch of different prescriptions that basically will tell you the star formation efficiency of these clouds based on their surface densities. So that gives me the sort of source of feedback in these clouds. And I can draw out where the sort of realizable part of parameter space in these, in reality. So you can see that down here, this is for Krupa IMF average feedback properties at solar metallicity. Down here, this is sort of the parameter regime of typical Milky Way GMCs. And you can see that in this regime, winds and photoionized gas are about in equilibrium with one another, okay? So this is telling us that in this regime, these things are pretty comparable to one another. Here I'm just showing, this is the surface densities of the clouds. Again, so 100 solar masses per square parsec up to 10 to the 4 solar masses per square parsec. So from, again, normal GMCs up to sort of the star-forming environments of like the centers of massive galaxies or what might be present in the early universe. Here's that trapping limit that I was talking about. Again, only important in extremely dense. This is the point when winds are so dominant that they trap all of the ionizing radiation within their shells. And here I'm showing you the simulations that I'm going to show you, which I ran these simulations long before I made this plot. So I did not intend for this, but if you take the momentum enhancement factor that you get out of the simulations and you sort of plot where they should be on this plot, they're right at this point where the photoionized gas and winds are comparable to one another. And here I just wanted to show you, this is how all of this stuff would shift if you change so this is assuming that the winds are momentum driven, how all of this would shift if you change the momentum enhancement factor of the winds, which, as I've motivated, hopefully is a little bit uncertain where that's going to land. So we think that it's going to be order 1 to 10, but it can move around in the space a little bit. So the basic picture here then is that you have this early evolution phase where you sort of set up that initial picture that I talked about, and then the two bubbles are kind of independent of one another, evolving on their own until they come into equilibrium with one another. So here I'm showing the gas pressure. So early times, this very overpressurized wind bubble within the surrounding photoionized gas. Here they're basically in pressure with equilibrium with one another, expanding together. So you can write down a semi-elliptic model for how these things should evolve. You can do it assuming both energy-driven or momentum-driven bubbles, and in the papers I just submitted, there's both of them, but I'm just going to talk about the momentum-driven solution. This is showing basically, this is a bunch of dimensionless stuff, so not very physically meaningful, but this is sort of the time as a fraction of the dynamical expansion time of the photoionized gas. So here being sort of when photoionized gas starts having an effect. And this is showing the radius of the wind bubble compared to that equilibrium radius. It has this scale factor so that all of these things line up on this classical solution. So if there was no photoionized gas, everything would follow this black line. And then this parameter is changing the relative importance of wind bubbles and photoionized gas. So very, very weak winds are this low zeta, so 0.1, up to very nearly just as important wind bubbles and photoionized gas at 0.99. And you can see that When winds are not important, the presence of the photoionized gas changes their evolution drastically. When winds are very important, they're not as affected. On the other hand, I'm only kind of doing, this is showing the evolution of the ionized gas radius. I'm only kind of exploring the part of parameter space where winds are inherently weaker. It's sort of one of these assumptions of this coevolution model. So in none of these is the ionization front drastically changed. It's all within maybe 10 or 20%. So that's less than 1 for sort of the dynamics here are not changed drastically. This is less than 2 on that front. If you calculate the amount by which the momentum carried by these bubbles is different than sort of the naive estimate you would get from just taking the classical solution for one plus the classical solution for the other, the changes may be within 25 to 30%. So in terms of a lot of things that one might care about, especially on the scales of galactic dynamics or galactic dynamic or galaxy formation simulations, this is not that important in terms of the dynamics, which is good to know. But I think the important things for these simulations I will show in a second. For these evolution models, I will show in a second. First, I want to test this simple coevolution model picture that I've come up with against some 3D radiation hydro, 3D radiation magnetohydrodynamic simulation. So here's similar to what I was showing you before, the gas density, the total pressure, so this will be including magnetic pressure, again, the cooling rate density, and the wind fraction. So now I have some photo-ionizing radiation. You can see the photo-ionized gas sort of, let's see if I try and limit to very early times. You can see this photo-ionized gas, which is overpressurized with respect to the surroundings, although it's not as clear on this color scale, and this much overpressurized wind bubble in the surroundings. And then as we go forward in time, that wind bubble comes into pressure equilibrium with the surrounding photo-ionized gas, and they expand together. I should say the assumption of the model is that it's a momentum-driven solution where I can assume a constant alpha p. You can use this equation that I was explaining before to actually measure the alpha p, the momentum enhancement factor, in these simulations, and they're not constant in time. So that's caveat 1 about comparing simple semi-analytic models to complicated 3D simulations. But if you take that into account, what I'm showing you here is a bunch of different constant alpha p coevolution models. This is sort of the mean one in the middle, and then sort of the bounds on either side. It's very rough correspondence, but it gets the basic trend correctly. The reason why this mismatch is wrong is because the momentum enhancement factor is small at early times, but gets large, but all of these things sort of start off at, the lowest one here starts off at as low as it was at the beginning. So it's good that it matches up at early times, that you would expect that, but the matching up at late times of the mean solution is good. Similar problems with the ionization radius. The problem that comes in here, and I'm explaining all of these things not to point out all the problems with my very simple model, but to motivate what will make a better model. It turns out the main problem here is that all of the messiness in the background allows the photoionized gas to occupy a much larger volume than you might expect from some mean density. So that changes things very quickly. It's also at very early times, I'm assuming that the wind bubble has no impact on the photoionized gas, but it does. It's sort of, the ionized gas does not expand as quickly as you would expect, because as the wind bubble expands, it draws in that ionization front, because it's sweeping up more dense gas that's recombining more quickly. That said, the total radial momentum, which is sort of the thing you might care about for the dynamics, is very well predicted by these simulations. But again, there's this resolution dependence, which comes from the fundamental unknowns of these mixing layers, really fundamental. Okay. The important consequences of these things. So when you include wind-blown bubbles and photo-ionized gas together, it does have drastic impacts on the observable properties of these clouds. So here I'm showing you the sort of emissivity-weighted ionization parameter. This is the distribution for simulations that are radiation only photo-ionized gas, and compared to simulations with winds and photo-ionizing radiation. And you can change the mean value by a factor of 3 or so. That can be hard to pull out of observations with all of the other uncertainties considered, but we have lots of really good observations of ionized gas clouds, especially with local volume mapper, where and a lot of that, a lot of the uncertainties, a lot of the discrepancies in those observations are thought to come from the messiness of these clouds. So my hope is that with future work, we can sort of use a better semi-analytic model that takes into account these the messiness more directly to sort of infer some properties based on the observables like from local volume mapping. And I'll just say that this change in the ionization parameter is basically the same amount of change in the ionization parameter that you get from radiation pressure on dust restructuring H2 regions, which is basically the same thing. The same thing is happening is you're pushing gas further away from the ionizing source so that the ionizing radiation field is lower, and you're making it denser. So it overall makes the ionization parameter much smaller. Okay. I went through that all very quickly. So here are the problems. Wind physics is uncertain, basically because of all of the uncertainties and problems in resolving the necessary scales in these mixing layers. Real H2 regions are very messy, they're inhomogeneous, and they're hard to capture with simple semi-analytic models. I've only included 2 mechanisms here, but really all mechanisms, so all the other ones that I've had listed here, direct radiation pressure, indirect radiation pressure, Lyman-alpha scattering as far as we do or do not understand that, are coupled at all times. And it's hard to make a direct comparison of our theory for the evolution of these things with observations, because even the extremely expensive, very, they're including all of the physics, 3D hydro simulations are unresolved in some aspects, and they're extremely expensive to compute. So my sort of wish casting of the way forward, the thing that I am interested in doing next is creating a more sophisticated semi-analytic model that will, when you create this, you can put into it a way to parameterize your uncertainty around the mixing layer physics, the dynamics of these wind bubbles. You can account for inhomogeneity, and I can talk about how I'm planning on doing that. And if you can implement that quickly enough with lots of different observable properties being output, then you can actually do direct comparison and inference for sort of precision kind of astrophysics, or you can at least get an idea of the degeneracies within the solution. You can actually start to fit things. So to leave up my conclusions, winds can still matter because even if they're momentum driven, they can be important for the dynamics of these star forming clouds, especially in I didn't even emphasize it, but as should be evident from the plot that I showed, in this high density star forming environments, winds are very, very important. And those are in the centers of massive galaxies. They are kind of should be one of the dominant feedback mechanisms. Convergence isn't always what it seems, which is the word to the wise on everybody who runs simulations. And hot feedback is particularly hard to resolve in this regime. But the way forward on that front is both either just direct comparison to the data through these semi-analytic models that I was talking about, and learning about the properties of those feedback mechanisms of that mixing layer physics from there, or better calibrated subgrid models, which are based on resolved simulations. And I can talk about my plans to do some of those if I have time. But for now, I'll leave it there and take any questions. Thank you.
Thank you very much. Do we have any questions?
So, departing from the basic spherical outflow model, in some cases, star would still be accreting at the beginning of this process, right? So you'd be seeding some strong inhomogeneity in the shell, I guess.
Mm-hmm.
Is that dynamically important at all later on? Or does it tend to just forget about that?
I don't think you need any, I don't think, so in the cases where you don't have magnetic fields, there's enough messiness there that you will have enough structure to drive turbulence enough that all of that will still happen. You can put in more messiness seeding in the actual wind that might introduce some interesting X-ray hot gas structure closer to the wind source, but it won't change the nature of the turbulence very much. In the MHD, over most of the range of evolution of these bubbles, I don't think that extra turbulence from stuff like that would be enough to save you from how over magnetically dominated the shells of these wind bubbles are. So I don't think including something like that would make too much of a difference.
Well, I guess just one more random question. So at the center of a massive galaxy where everything is, I guess, significantly obscured and so on, but you might have more than one of these clouds or star clusters forming. And what would happen if you had one of these massive star clusters just falling into a molecular cloud? So, you had something that hadn't formed stars, but they just collapse into each other. Would the cloud basically get disrupted as the collision was occurring?
It would depend on how bound that cloud was. And usually these things are, in the clouds that you're talking about, the timescales for star formation are, the freefall times are quite short, especially compared to sort of the dynamical interaction time with the surroundings. So you kind of have these clumps that form and start forming stars very quickly, and feedback is, it's very hard to disrupt those clouds. So they form they nearly kind of turn everything into stars very quickly. So yeah, you could imagine another cloud coming by. I'm not sure that the feedback is just doing enough to disrupt the cloud that it's living in. I'm not sure it would do much to disrupt that.
Well, I guess just to clarify, in simulations showing us how many dynamical times from the initial collapse are being represented?
In the simulations that I have that are relevant to the things that you're talking about, those are run for maybe 12 freefall times. But the freefall times in those things are like half a mega year. So, yeah.
So about the lifetime then of a massive star.
Yeah, you cover many, yeah.
Can I ask you a couple complications?
Sure.
One being, how important is equilibrium ionization and cooling in the process? So you mentioned CIE cooling.
Mm-hmm.
So if we were to consider non-equilibrium ionization, how much does that change the
So the first simulations I showed were not in equilibrium. The radiation simulations and all of the my simulations in the past 3 years or so do non-equilibrium hydrogen photochemistry. In the hot gas, it's still CIE. So my thought is, having talked with Emil Sternberg, who's run a few of these mixing layer simulations in non-equilibrium, is that it's like a 10% effect. So it doesn't seem to be huge, but I haven't done those simulations myself. Yeah, that's the only intuition I have of which to base that.
Another quick question. When you have photo-ionization and the winds, you might imagine that you get a bit of like pre-homogenization of the environment by the photo-ionized gas pressure. In which case you might expect the alpha P to be higher.
Yes.
Do you see that?
Yes.
Okay.
Yeah. So I didn't get a chance to talk about it, but you're exactly right. You heat everything up to the same temperature. It's at different density. It's at different pressure, so it just smooths out. You can measure the fractal dimension. If you compare the fractal dimension of the wind interface in the pure hydro simulation to the hydro plus radiation, it's much smoother in the hydro plus radiation than it is in the pure hydro, and it's because of that. Yeah. Great. And you get a larger alpha P because of that.
I have a question. Do you expect jets to make a difference in these coevolution models?
At least on the scales of which I'm thinking, which is sort of these massive clouds and the disruption of the whole cloud, energetic. These sorts of scales that I'm thinking, they would kind of just add an extra mechanical energy input, and their energy would not be that important compared to the host stars. So on smaller scales, in individual star forming regions, obviously they're important, but at least in this picture, I don't see them being that
You can't have a spatial distribution.
Sorry?
Can't you have a spatial distribution which makes it closer to the edges, for example, of that bubble?
Like putting forming stars with jets near the bubble edges? I mean, you definitely see jets around sort of bubble edges in star forming regions, but I don't think they're sort of dynamically important for the expansion of the bubble overall.
Maybe we can continue discussion upstairs over some, hopefully there should be cookies there. Let's thank our speaker again. Well, and during Zoom, check if anybody was asking questions.
Were there questions?
I quit because I turned off the volume on my phone, but apparently that doesn't turn off the volume in the browser. So let me just.
I should have checked the Zoom.
I think it would have cropped up on your screen. Somebody has something. Just close this note. Yes.
Is that comprehensible?
Yeah. I was a little confused by the